Good evening. Welcome back to Vegas October 1 Sounds. Uh, Tonight we're going to drill down deeper onto the Volley 7 Talking's guns. I had a couple of commenters ask me to refine my statements a little bit and provide more data and an expansion upon what the data means. And in particular, one of them wanted to see a lag map for Volley 7 showing that the muzzle was sweeping or changing directions. I haven't done too many of those. So what I did was two things. One is I took the sonic visualizer session where we showed the Volley 7 near the VIP area, and I ran it through filters such that this section, right after the end of the visible sonic cracks, has had the lower frequency things below 3000 removed, and then an amplification was done on it so that I can see the signals that are hidden within. And here you can see that just past the last goods one, we see one that's a little bit less, and then we've seen these two blips, and if I shrink it down, these two blips over here. And then it gets really hard. You can see another really faint one down here on the log frequency plot, and then after that, well, it's anybody's guess. So here you can visually see how the strong signal on the sonic crack faded out. It didn't just disappear. And it faded out relative to the intensity of the muzzle blast. And so that makes it basically become invisible to the regular analysis unless you suspect something being there and can apply these filters. Now that's the one phase. So that gives people a little bit more comfy feeling that it's not just hocus pocus. So the next thing that I ventured out on was to create a lag table for the Volley 7. Well, obviously, hang on a sec, let me save this. Now I can save it. I didn't want to lose that session. So anyway, so what I ended up with was something like this. What I had to do was go out and find a Volley 7 where I could see all the lags for every shot. And of course I fell back on my favorite, which is Oasis Apartments, where even though it's 1,000 feet or 1,700 feet down the road, it still has real good signal for both the muzzle blast and the crack. Oh, somebody's being hauled away here where I live, or near where I live. So anyway, it has good signal. So I marked every crack, recorded their times, and of course I already have the muzzle blasts, and then I calculated the lag for every shot. Now at the Oasis Apartment, the lag is pretty small. It's in the, well, here we can read it right from this graph. It's in the 20 millisecond to 60 millisecond range. And this is just Volley 7. And Volley 7, of course, is a little over 8.5 seconds. So once I had that, and we can make this plot, then we can look at things. And so we're basically going to go over this and extract useful information from it. Well, first off, I made a mistake there, and I have yet to correct it. So then we see that on this graph, lag increases as you go up, and time increases as you go left to right. So at the front of the volley, we have these kind of lags, and at the tail of the volley, we have these kind of lags. And so, with respect to Oasis Apartments, the greatest lag occurs here, and the smallest lag occurs here. And so you have this huge difference, relatively speaking, over these, so I don't know, 20 some shots. And this is a pretty good drop here also. Now what this says is that at this point the bullet trajectory was furthest away from Oasis Apartment, and at this point it was its closest. Now what that closest and furthest means, that's a calculation that involves a lot of math, and I don't think I could just do it here on the screen. One is because I'm prone to errors in doing complicated math by hand, and the other is I need to be repeatable and applied to many things, and that means, you know, a program or a piece of software to do it. But that's diving too deep, and when we start getting into that level of stuff, you know, we're down into rocket science material. Right now I want to keep it so that you can look at this graph and get a feel for what it means. So again, up here at the large lag we are closest to Oasis, and down here we are furthest. So we can look at this and say, okay, we were somewhere in between those two, large and small, and then we started gradually coming down. Then all of a sudden we start getting further and further away, and then we go back up closer, and a little bit variation. Then we continued until we reached the closest point, and then we drop back down and settle into this nice little oscillatory pattern here. Okay, so what does this say? Lag is a function of the bullet trajectory, and if the bullet trajectory is changing and Oasis is staying fixed, then all the lag generated is a function of the bullet trajectory. So by this simple graph we can see that the bullet made some pretty, or the trajectory of the bullet, and hence the direction of the muzzle, made some pretty big changes relative to Oasis Apartments. Now once again I'm going to repeat, you cannot tell from this how big that distance is, and in fact it's not linear. By that I mean that if I went from 2 to 4, 20 to 40 milliseconds lag, that does not imply that the distance doubles or anything. It's a trigonometric function based upon either the sine or the cosine, well, any way you want to put it, you can express it, relative to the cross distance, or the distance from this point at Oasis Apartments to the trajectory of the bullet. But I don't want to get into that because it really complicates things, and that's just for lag. And when we start talking about volume, there's two more equations that are equally as maybe more complex, in fact, for us to determine at a certain lag what would be the volume for the muzzle, and what would be the volume for the lag, and what would be the difference between them, and who dominates and what do we hear. That's truly rocket science. But we can also make some other observations here. These little dots right here, I mean, that's probably a case where 4 bullets hit the same target in a very short period of time, because there's no change in lag. Now, lag and distance are three-dimensional phenomena. For example, you could have a lag of, let's just say 40 milliseconds, and that could equate to, this is hypothetical now, 400 yards from where you're at to the bullet trajectory. But that bullet trajectory is a three-dimensional thing, and it can be, you know, that many yards at ground level or that many yards up in the air. Either way, they would all produce the same lag. So this indicates that it probably hit the same target, but doesn't require it that it hit the same target, because you could have that 40 millisecond lag on the ground, hit somebody, and then jump up, the barrel will be rising up, and the next shot, even though it's the same lag, will shoot over the person. But in general, I think it's more likely than not that these 4 shots hit the same target, and correspondingly these 2 did, and those 2 did, those 2 did, and that jumped over to a little bit further away, those did. So, you know, there was some pretty high potential for Volley 7 to do damage to individual specific targets. These types of things up here, you know, since there's some big change in lag, they're going all over the place, but they form a beat pattern. These would form a beat pattern right here at the average distance that this lag represents. whether be it in the air, on the ground, or anything. And similarly, this average distance. But that leaves us with the middle. Okay, so if we go back and say, well, where was that volley for the VIP tent in relationship to the timing of this? Okay, let's see. We got two pictures here to show you. Starts. This is the spectrogram, as you obviously will realize by now, for the VIP, and I measured the time from the start of the volley itself, and here you can see the muzzle blasts, then you see the sonic cracks, and then it goes back to muzzle blasts, and you can just barely see in there those three things that I talked about. And it starts, these cracks start about 4.2 plus or minus a little from the start of the volley. And if we go back over to the other map, which, here we go, 4.2. So 4.2 is right around here. So if we draw a line straight up there, then we're going to start right here. Okay. So that means that the cutoff point would be right about here. Well, that would intercept a number of, if that were true, let's say, then what we should hear is these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for sure, 12, this one over here, 12, 13, 14 total for sure, and maybe 4 more for a total of 18. Oh, and I closed down my session, didn't I? Oh well. Can we count them with this? Yeah, we can probably look at this enough to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So, looks about right. We'd also note that we have one there, and we have one there, and one there. So we got 3 or 4 others that we can probably see here. Does that correspond to anything? Well, if the limit is right there, and we'll get back to that in a moment, then we're probably going to see this one, probably going to see those, and they should line up approximately. We have to remember that this picture involves not only the timing of the lag, which we can measure, but it involves the volume of the sound. And the volume of the sound is a function of both distance, the propagation form, and a couple of other phenomena. So for example, with the muzzle blast, it's pretty much an inverse square formula, where if you double the distance you get 1/4 the volume. Volume being kind of a nebulous term here, because it's really energy per square area that we're talking about. But with the supersonic crack, it's not so simple. There's actually 3 regions from that conics wavefront that produce different decay rates. And so in one case you'll have a fairly linear, and then it will jump to a smaller one, and then it'll change to a approximately inverse square relationship. So just because your lag doubled, you don't necessarily have any real good feel for what the actual volume is. So we use this rule of thumb that if the lag is bigger, it's closer, and the volume should be higher, or the intensity. I should stop using the word volume. And that's, the engineering first order approximation to what it's saying. But underneath, if you start relying upon that to make real finite calculations, you'd better go to the formulas and do some real calculations. And the same is true of the lag statement, that as the lag gets bigger, it's getting closer. That's also a first order approximation, and if you need the exact footages and real ratios, then you should go look at the formula. Alrighty, so if we hop back over to this other picture, there we go. So we ascertained that, yep, sure, the level was right here, but what about these 3? Well, that's a problem, because they drop below the threshold at which we believe that we should hear them. But we have to also consider what I just said, is that the volume or intensity is a non-linear phenomena. And therefore, as the weapon was sweeping, this nonlinear process comes in, and the sound of the crack gets to do different things, and there's probably a real good reason why we can still hear these. All right, so now let's get back down to the core of the crux of the matter. How is this muzzle sweeping? Well, first off, we've established that it's not stationary, and that can tell you a whole lot about what's going on in this thing. And we can see that it's not stationary. It's all over the map, and that it's oscillating, and that it's going up, down, left, right, and center, although I can't really tell from this. I would assume that unless there's some specific restraints to the muzzle, that it's equally as likely to go up and down as left and right, although that depends upon the weapon. So which way was it sweeping? Well, we have to bring in more information to make that ascertain that. With this, we can probably say that, well, if it's furthest or closest to us there, then it must have been sweeping away from us and towards this. Well, what is this? That's the VIP tent over there. So let's bring up a graph here so we can see what's going on. All right. Where am I here? There we are. I think I went too big. Alright, we're getting close now. So I think this is the one, yeah, that's where that pulse is seen. And we're claiming that when those bullets were there, and they obviously were hitting something, that was the furthest distance from Oasis Apartments, which is way the heck and gone down over here. Where's the bullets? Right here is where we're looking to. I mean, come on, you can see how far these things can be heard. All right, and that the trajectory path was sweeping towards Oasis from that furthest reach point, which means it would be sweeping down towards this way, the stage. Okay. Well, how far it sweeps, that's again a complex calculation, but given that the lag is still relatively small, I doubt that it swept anything even past Mandalay Bay Road there. So probably less than 25 degrees, maybe less. And you can say, well, if you can record that down there, why does it change so much? It has to do with the relative volume of the muzzle blast. We're over here and we're really close to the Mandalay Bay, and while we don't have a direct line of sight to it, we're still close, and the muzzle sounds are loud in this venue. The noises are loud and everything. So any degradation in the sonic snap starts hiding it behind these loud noises, and vice versa. When the sonic snap gets close and loud, it hides the muzzle, even though the muzzle is just ripping and roaring. So it's the ratio of those volumes, and as I expressed, calculating what the absolute value of those intensities are and the ratio is a very complicated thing. So we can't just look at that graph and say, oh yeah, we should be able to hear it. But now when we look at the spectrogram, we can kind of get a better feel for it, because it does measure intensity. Alrighty, so if that were true, then if we were sweeping from what is essentially northwest to southeast, then we should also hear a similar phenomena by the stage. Well, let's pick, I think I picked this one, didn't I? No. I'm looking for Volley 7. There we go. Behind the stage. Alrighty. So if we go locate behind the stage and look at it, let's see what we see. Of course, I'm going to look on my machine. because there we go. These are Sonic Visualizer sessions which I've saved. So, behind the stage. Okay, so here we are. Behind the stage, Volley 7. And as we can see, it starts there and ends over here. And in the middle, we have a very similar phenomenon. How many shots this time? Well, this time we've got 1, I don't know, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, about the same number of shots. When did it start? Well, first we'd have to know where the beginning was. And this one's a little trickier. Okay, pull up our time measuring tool. Maybe there. Maybe there, go into there. Bring that back in a little bit. I don't know if it's there. I think it's out there. I'd have to be real careful to get this measured. So about 4.31, or about 0.1 seconds after when it was at the VIP. So I'd really have to do a little bit more accurate measurement here, but my first estimate here would say that it was at, sweeping from the VIP to the stage area in 1/10 of a second. So let's go look at our graph and see if that looks anything near what the data points tell us. Alrighty, so how many bullets did we have? Well, we know the bullets are going at about 10 per second, so 1/10 of a second will be only one bullet, really. Let me double check that. 1/10 of a second start is 100 milli. Yeah, that would be only one bullet. So for that one, then it would probably just go down here and pick up one more of these, and it's essentially measuring the same thing. But because the anyway, it doesn't matter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, probably was or 21. So I would say somewhere between 18 and 21 of these things right there again got measured there. So that makes sense. Now, I would, if I were going to drill down way deep, I would continue to do this. I would continue to put lag plots for everything I could measure. And then I would start doing some complicated calculations and verify that, yes, indeed, it was sweeping that direction at that rate. So, once again, real data gives us a much better idea of what was going on, even though initially we did ascertain that it was, or propose and hypothesize that the decrease in intensity of the sonic cracks was due to the muzzle sweeping to and from the VIP area. In this case, we can see it swept. Now, if we go back to our map, yeah, let's shrink this down. You know what? I should bring up my lag map because it's less cluttered. But anyway, we can do it here. So in this case, it probably was sweeping. It probably was initially firing in the venue, swept up, and then came back down, and then went this way and settled in right around here, oscillating back and forth. So I would expect that most of the bullets ended up in here, but I'd have to do those absolute value calculations to verify that. But I'm pretty confident now that the muzzle was sweeping. This was the furthest point away from the Oasis apartments. It swept down this way in fairly short order, and you saw on the other graph the rest of the phenomena. So, is there anything else I want to say about this? Oh, I'm sure there is, but I don't see it right now. Anyway, I'm going to call it a wrap on this subject matter, namely Volley 7, the sweeping barrel, the talking guns myth exposed. It's really just, I know what I'm going to do. not every area that's on the map is noisy. If we go to a quiet area like Oasis, we get a better indication of what Volley 7 was doing. And there are other areas we can look at. So let's go back over to our trusty map here and start pulling away from the venue. And by pulling away from the venue, we're losing all the sounds of the chaos going on there. And we come down here, and we got this, and we got another hotel down here, Hotel 8 or Family Hotel, and there was a recording made at that. Let's see, I don't know if it's even on this map, but anyway, quite a while ago, a fellow produced a recording with the Family Hotel right across the street on the south side of Mandalay Bay, and they recorded Volley 7. And I'm going to pull up that sonic visualizer session, and it's going to be kind of interesting. Oh, I thought I saved it in a different format. No, that's not the one I wanted. Well, food bar. Having a little bit of difficulty locating it in here. Give me a minute. I will find it. Because I don't believe this is it. No, yeah, it is. There it is. Okay. Yeah, this is it. Everything's all wonky. So let's get all this set back down to the correct. I left it in a bad state. Alrighty. And over here, the waveform. It's purple, huh? Okay. It's purple. That doesn't look purple. Alright, and what we're going to do is if we go to the end of it, you can see that we have something which is Volley, looks like a Volley, and it is Volley 7. So what I'm going to do though is had to pause it a moment there. Anyway, we're back at Volley 7 at the Family Hotel across the strip from the Mandalay Bay. And we see that there's a nice set of sounds here, which I've already identified as Volley 7. And let's listen to them. Okay, there's one sound for every shot, or so it would appear. And we don't have the typical muzzle sonic followed by muzzle. So let's look close. Now this is just a power up there. So what I'm going to do is rely upon the waveform in this case to show me, because it's kind of interesting. So if we look really, really close, and let's get rid of that one so that we're not having to muck with it. And let's make it blue in this case. Alright. If we look very, very close, we see for each sound that we heard, we see a group of 2 sounds here and 2 there, and they're obviously related because that one and that one look very, very similar. That one and that one look very, very similar. These are about twice or 3 times as wide as those. Well, guess what? This is the muzzle blast, and this is the sonic shock. This is the sonic shock. This is the ground reflection. This is the direct path muzzle blast. This is the ground reflection. So you just can't get away from this 2 or more sounds per bullet, or per round of fire. Only here they're so close together that the ear and the brain hear them as essentially one. But we could measure, once again, we can measure the lag. Okay, measure tool there. So we go from the very start of that one, the sonic, to the very first indication of the muzzle, and we end up with about 7.6 milliseconds, which is getting essentially 0. So in this case, you know, we've got a whole series of these things, and we can look at them, and we can, this time we're going to, and this is a stereo channel. I normally deal with mono so that I can get away from all the duplicate peaks that these things generate. But at this scale, they look like just one signal. But if we watch this as it goes by, we'll see somewhere along here something different. Let's just go right towards till we see something. Oh, up there it started looking a little different. A little change in the shape. In this case, the sonic crack got louder compared to the muzzle, and they're further apart. Okay. How much further on here? They get way apart. All right. So here at the tail, there's bigger lag, which means, you know, it's getting closer, and the sonic shock is bigger than the ground wave reflection, and the direct path of the muzzle shot is about the same as the ground reflection. And the lag, if we measure it, is 6.8. That was just about what it was. It looks different, doesn't it? Did I measure it wrong? A little bit. Nothing starts right there. Oh, wait a minute. Yep. And over here, yeah, it measured a little bit off. You got to be careful there. It starts right there. So in this case, it's 200 microseconds longer. And what about the next one? That one's a nice big old fat signal. And it's going to be... Well, you know, see, this is one of those cases where it's hard to determine where it starts. Yeah. I don't know. So I'll give up on that measurement. So let's look at the intensity overall. So the lag was so small as, you know, we're going to have to measure microseconds to determine the difference in the lag. So that's not very feasible. So let's look at the intensity of the sounds. Here we see a little bit greater intensity, and if we turn the intensity up, we can probably, yeah, okay, so here we see more intense, a little bit more intense, a little bit more intense. So what do we see? Oscillations about every 1, 2, 3, 4, 5, 6, about every 10 bullets. Okay, there's 4 sets of oscillations there. There's a fifth, only this time it's much, much bigger. So whatever it is just got, oh, that's the start of it. The front is closer, way closer. Then it dies down a little bit, and then it does its thing, so it increases, and at the tail it's oscillating. Sound familiar? And in the middle, it's the least amount of volume. So if we measure this, okay, alright, let's go to 4.2 or so. So right there, we see over here is the tail end oscillations, and in here we have 2 quiet areas. In the middle we have a little bit more, and if we bring up our lag plot, okay, at the end we have some oscillations where the bullets get closer to the oasis, so they'd be getting closer to us. Up and down, 1, 2, 3. I said 4, maybe that's the 4th. And then for that area that shows up as a pulse of 13 on the others, there's should be 2 quiet areas. Where are they? 1 here and 1 there. with that thing in the middle and that thing in the middle, and at the start it's closer to us, but not as close as at the tail. So, you know, it superficially and qualitatively kind of matches the lag plot there. But, and this is the thing that should be obvious to everyone by now, is it's one continuous volley. There's nothing overlapping in there. There's a straight number of shots, which I think in this case is 95. One volley, one gun, its muzzle is moving. The sounds are created by the dynamics of gunshot acoustics. I think it's case closed myself. Also in this is one of the few videos that include gunshots where you have this beautiful, beautiful example of harmonics from the sirens of the cops, because they were right there. You know, it's only 30 feet away. And here you have two of them and they're overlapping, and it's just really, really, really beautiful. Oh, this is interesting. Something up there I hadn't seen before that I want to look at. This dark area is where somebody spliced two pieces together. I don't know what that front does, because that kind of looks like gunshots, but if we open it up big time, you see that it's not. It's just some sort of electronically generated sounds. I don't know what the hell that was. But while we're here, I want to look at something that I haven't looked at before. I want to look at the background up there. There's a couple of things that bother me. You see that band there? That indicates something is going on either from the original recording or from a re-recording, but yet there's no real flat lines otherwise. And it's carried across from this thing, which obviously was not a part of that recording. So that's potentially a function of the upload process to YouTube, or the codec in the software used to create it before it was uploaded. And as you can see, there's another band up there. And if we change the color on it to, I don't know, ice, let's say, and we drill down hard, and we set the resolution high, well, maybe not that high. Oh, let's go over to a different set of spectrogram here and do the same thing. Nah, I'm not going to get anything else out of that. Okay, so that was the end of that. Anyway, that's a wrap. On to the next video, and we see you in the next one.